Thank you very much for the nice introduction, and thank you very much also for giving me the opportunity to present our work. So partially that will be a collaboration between the University of Cambridge, Harvard, and Delft. So I'm going to mention the interfacing of spins and mechanics using a specific color center in diamond called the silicon-vacancy center. So we're all familiar that the quantum technologies these days separate roughly into three categories between quantum computing, which provide hopefully an exponential speed up in processing certain tasks, quantum communications for physically secured communication, and quantum sensing, with a variety of physical systems that can be used as qubits, and we're going to focus on the atomic impurities for the next part of this talk. So, as I said, the silicon-vacancy center is a color center in diamond, but why diamond? It's an excellent host. First, it has a very wide band gap of 5.5 electron volt, meaning that if you want to interface some system with light, your matrix will not interfere that much with it. It is a spin-free lattice with 98.9% of the carbon atoms constituting the diamond, which are spinless. And you still have enough nuclear spins from the carbon-13 to use them as long-lived memories. So it is a host to a wide variety of atomic impurities with discrete energy levels lying within the band gap, and so you can interface them with light. So they pretty much act as single atoms trapped into a solid-state matrix, so you can get rid of all the complicated trapping mechanisms that we've seen before. So far, the most investigated color center in diamond to date is the nitrogen vacancy center that you can see here. With in the carbon matrix, you remove two neighboring carbon atoms and replace them by one nitrogen atom sitting at one of the carbon sites. And so it's been so popular because it possesses a spin 1, electronic spin 1, and is optically active. And so far, there has been a lot of progress to the state-of-the-art, especially in quantum sensing, with magnetometry in particular, where a single nitrogen vacancy center is embedded into a diamond AFM tip and was used for sensing various magnetic structures, including fermions. Another sensing experiment was done by doing thermometry using NV centers in nanodiamonds incorporated into living cells. But those are not the only applications. There are also electric field sensing and also structural analysis of molecules. And all these applications stem from the fact that the NV center, by being an atomic scale sensor, provides a pretty unique resolution, spatial resolution. In terms of quantum networks, there has been a lot of progress, including recently with two back-to-back articles from the group of Ronald Hansen in Delft, where they had a 3-node network, quantum network, with NV centers in each of them. And what they did was entangling the 3 nodes and realizing teleportation between 2 of the non-neighboring nodes, which hadn't interacted with one another. And all of this is made possible due to the fact that the NV center possesses a long spin coherence time. However, the entanglement rates that are achievable with this system is quite limited due to the fact that the NV center emits very few usable photons into the zero phonon line. So if we have a closer look at the fluorescence spectrum of the NV center, you have this sharp peak, which is the zero phonon line, and corresponds to photons that are coherent with the electronic spin state of the NV. And they constitute only 4% of the total emission. All the rest, the big blob here, are incoherent photons that can be used for reading out the spin, but not as vectors of entanglement. Furthermore, the NV center has stability issues when incorporated into nanostructures. So for scaling up, that's not the best solution. So this is where the silicon-vacancy center comes in. Also a color center in diamond, where you remove 2 neighboring carbon atoms and replace them by 1 silicon atom. And we study the negative charge state of the system. From the fluorescence point of view, the SIV shines due to excellent fluorescence properties, unlike those of the NV. Its emission is concentrated into a sharp zero phonon line at 737 nanometers, with about 70 to 80% of the emission into the zero phonon line, as opposed to 4% only with the nitrogen vacancy center. And furthermore, due to its symmetry, it has an inversion symmetry, it is stable in nanostructures. On the spin side, the SIV possesses a spin 1/2. So if we look at the energy levels of the SIV in the presence of a magnetic field, our spin qubit are the 2 lower lying spin states. And so this spin state can be controlled either using microwave pulses or even all optically. However, this spin state suffers from decoherence and decay at 4 Kelvin due to single phonons that excite the qubit to a replica of the qubit lying 50 gigahertz above. So you have your qubit nicely sitting in those levels, and then a phonon comes in at 4 Kelvin and kicks them out here, and that causes dephasing. And that was evidenced by just looking at the temperature dependence of the dephasing rate of the spin in blue here, and comparing them with the rate of excitation between those states up to those states. Those are the gray points, and you can see that they nicely match. So at 4 Kelvin, that's the dominant dephasing source for the qubit. So you've got pretty much 3 options. Either you have a lot of money, like the group of Misha Lukin, and you directly buy a dilution fridge, which is what they did, and you work at lower temperature directly at millikelvin. Or you alter the phonon density of states at the frequency of the phonons leading to those transitions, so about 50 gigahertz. That is very challenging from a fabrication point of view, because the structures that you need are about 120 nanometers maximum. Or the third option, and that's the one that we've chosen to follow here, was to split those 2 states, those 2 orbital branches further apart from each other, so that there are no phonons to excite them. So in collaboration between Harvard and Cambridge, we made diamond cantilevers with electrodes on top and at the bottom, and SIV centers implanted at the clamp of the cantilever. And so what happens is that when you apply a voltage difference between the top and bottom electrodes, the cantilever deflects and strain is applied at the location of the SIV. And this way you can actually apply tunable strain. So if we look at what happens when we apply this strain to the energy levels of the SIV, you can see that they split apart from each other, as you can see here, which is exactly what we want. And so we start from a ground state, from a ground state at 50 gigahertz to almost 500 gigahertz. So we increased it by about an order of magnitude. While doing that, we realized that the SIV has actually a quite remarkable strain susceptibility with susceptibility of the order of petahertz per strain for the orbitals, so those two levels, and for the spin state, 100 terahertz per strain, which is like 4 orders of magnitude compared to the envy center, for example. Then what we did was, since we've split the orbital branches further apart from each other, we measured the coherence time of the spin using coherent population trapping, whereby we shine one resonant laser between one spin state and one excited state, and we scan another laser resonant with the other spin state and the same excited state. So the two ground state spin states and a common excited state. And so what happens is that when the second laser becomes resonant with the transition, one of the eigenstates of the system is a superposition of only the two ground states. Despite the fact that you have two lasers exciting the system goes dark because of this eigenstate, which does not include the excited state. So when you're scanning, when you hit the resonance with one of the lasers, you get a dip in the fluorescence counts. And as we repeat that as a function of the applied strain, so when we're splitting the two orbitals further apart, you can see that the CPT dip, the dip in fluorescence that we see, gets narrower and narrower, actually revealing two dips that we ascribed to the presence of a neighboring carbon-13 spin. So why is it interesting? Well, the fact that the CPT dip width is directly proportional to the spin dephasing rate. So if we plot the CPT dip width as a function of the ground state splitting, you can see that it's going down and finally saturates, meaning that our spin dephasing rate decreases with the ground state splitting. And this way, we could actually extrapolate at very little laser power that our spin T2 star reaches 250 nanoseconds at 4 Kelvin, which is very similar to the 300 nanosecond measured at 100 millikelvin. So using strain tuning, we managed to eliminate the dominant dephasing system at 4 Kelvin. The spin decay undergoes pretty much the same thing with an improvement by a factor 20, reaching 2.5 microseconds. So it's all very nice, but how about we actually capitalize on the very great strain susceptibility of the spin? Why that? Well, mechanical vibrations can be used to interface a wide variety of systems to form hybrid architectures whereby you combine the properties of the advantages of one qubit and the advantages of another qubit, trying to mitigate their weaknesses. And so taking advantage of a large strain susceptibility of the SIV, we use surface acoustic waves, which have several advantages. First, they're easy to generate using interdigitated capacitors. So you see these finger-light structures. They do not propagate in free space, unlike photons. So when you launch a surface acoustic wave on top of the surface, you know that it's confined to the surface. That also limits the crosstalk. If you make trenches, physical trenches, you can make easily a waveguide. And this way you can actually manipulate on-chip your driving system, and unlike microwave photons, for example, that can radiate everywhere. So this way, initializing the spin optically and reading it out optically, we could insert a surface acoustic wave pulse between initialization and readout and drive Rabi oscillations of the spin using the surface acoustic wave. Building up on this, we performed multiple pulses on the SIV spin, still using surface acoustic waves, and perform dynamical decoupling. So what it consists of, a first pi-half pulse creates a superposition of the two spin states. Then a succession of pi pulses, as you can see here, rephase the spin. And the more you do, the more you rephase the spin and eliminate the coherent sources in the environment. And so this way, by increasing the number of pi pulses from 1 to 5, for example, we can see by letting the system process longer and longer that the dephasing rate kicks in later and later with the increased number of pulses, going from about half a microsecond with 1 pulse to 1.5 microsecond with 5 pulses. However, you can see that you have, when you're scanning the precession time of the spin, you have big dips for certain precession times, and that's due to the presence of resonant nucleus spins in the environment. More precisely, we investigate a little bit more this principle by doing for the specialist an XY8 sequence, whereby you change the phase of the different pi pulses from X to Y and X again and Y and etc. To mitigate the pulse errors. And we scan the duration. We scan the duration tau between the pulses, between the pi pulses. And so what happens is that when a nucleus spin is, when the pi pulses are synchronous with the precession of one of the nucleus spins, you have, instead of having loss, rephasing of the coherence of the electronic spin, you actually have a buildup of dephasing due to this coherent interaction with the nucleus spin. So you're flipping your spin in sync with the precession of a given nucleus spin, and so you lose your coherence of the electron spin in favor of the nucleus spin. And so when you're scanning the interpulse delay, you have, at those resonances, big dips in the coherence of the SIV for those specific interpulse times that correspond to the hyperfine coupling with a single nucleus spin. And so this way, in this case, for those values of the interpulse delay, we can extract the hyperfine coupling with this given nucleus spin. So if the SIV can see the nucleus spin, the reverse is also true. The nucleus spin also feels what's happening to the SIV spin. And so you can think of it this way. You have the nucleus spin that is processing in an external magnetic field. And with the hyperfine coupling to the electronic spin of the SIV, the precession axis changes ever so slightly depending on the SIV spin state. And so when you switching between the two spin state of the SIV, you're switching between these two precession axes for the nucleus spin. And so if you time the switching between the two SIV spin states cleverly, you can do half a rotation of the nucleus spin, then switch the spin state of the SIV, so you switch the precession axis for the nucleus spin, and let it evolve again by half a period. And so little by little, you're tilting the nucleus spin. And this way, you can actually control it by just flipping the SIV spin in sync with its precession. And you can even perform pi-half pulses on the nucleus spins, the sign of which depends on the initial state of the SIV. So then moving on to a more complicated pulse sequence, so you don't need to understand exactly what's happening, except for the fact that we're only doing pi pulses, series of pi pulses on the SIV. we can simulate what this sequence does to the nuclear spin, and we can see when we plot the state of the nuclear spin as a function of the interpulse delay, we can see that we can, for certain interpulse delay times, we can initialize the nuclear spin depending on the initial state of the SIV. So for example, if the SIV was in the spin state down, we do this whole pi pulse sequence, and if the interpulse time between those pi pulses is, say, about 1.57 microseconds, at the end of this sequence, the nuclear spin is in state up. So we perform experimentally this sequence as well as its reverse that acts as a readout sequence. So with this first sequence, you transfer the spin state of the SIV to the nucleus. That sequence does just the opposite, transfers the nuclear spin state to the SIV to be read out. And so when we simulate, which are the solid lines here, you can see at the end that we expect to measure the SIV spin state in a certain state, depending on the, how the nuclear spin was initialized. And we can see experimentally with the data points that we match these predictions pretty nicely, meaning that we did manage to initialize the nuclear spin and then read it out, using, again, only mechanical pulses on the SIV. Building up on this, so we then use these sequences to initialize the nuclear spin, and then do, again, a series of pi pulses on the SIV with varying numbers of the pi pulses. And this way, we can actually drive Rabi oscillations of the nuclear spin. And so this way, we've proven that we can mechanically, via the SIV, control the nuclear spin, which hadn't been done so far. So that's pretty nice, especially for the fact that to do those Rabi oscillations with about 15 kilohertz Rabi frequency, which is pretty standard for coherent control of nuclear spins, we needed to use 2 orders of magnitude less power compared to other control methods that rely on radio frequencies or microwave driving. So that's pretty nice if you want to scale up the system, because usually when you're working at very low temperatures, less power means that you can put more, you're heating less in your system. And so you can add more qubits. Just to check that we are dealing with a single nuclear spin, we did a Ramsey sequence on the nuclear spin. So what we do is we initialize the nuclear spin, then put it into a superposition of states using, again, pi pulses on the SIV. We let it process for a certain amount of time, and then do another pi pulses and read it out. And during this free precession time, we either put the SIV in the spin up state or in the spin down state. And due to the fact that you have hyperfine coupling between the SIV and the nuclear spin, you have a different precession frequency of the nuclear spin, depending on the spin state of the SIV. And this is exactly what you see in red and blue, depending on the spin state of the SIV during the free precession, you have a different precession frequency that nicely matches the hyperfine coupling. So then we increase the free precession time all the way to 2 milliseconds, sorry. And you see that the Ramsey fringes don't lose any visibility, even up to 2 milliseconds, meaning that the nuclear spin remains coherent after that time. Then we do a spin echo sequence, whereby we perform between the 2 pi half pulses on the nuclear spin a pi pulse that will rephase the static noise. And this way we show that the nuclear spin doesn't lose coherence even well above 10 milliseconds. So that shows that despite this new way of controlling the nuclear spin, mechanical driving of the nuclear spin, this doesn't affect the coherence time of the nucleus. So the nucleus can still be used as a good quantum memory. And since I have a little bit of time, I just wanted to flash some recent result obtained with the group of Team Tamino in Delft, where we studied nuclear spin pairs. So this time, this is a single SNV center that is used as a probe. And what was studied was nuclear spins that are very close to each other, very proximal nuclear spins in the diamond lattice. And such a system can actually be thought of as a single qubit where the up-down and down-up states are the two pseudospin states. And when you do a Ramsey measurement, so just let the system process, we found almost 2-minute coherence time, which is the longest coherent time found in the solid state. And this is due to the fact that you have a combination of 3 factors that all play to increase the coherence time. First, because of the nature of those states, down, up, and up, down, you have a decoherence-free subspace. You also have, we're also dealing with clock transitions, so you are, to first order, insensitive to magnetic noise. And finally, you have fast nuclear spin bath evolution, so all the other neighboring carbon spins move very fast compared to the precession frequency of the nuclear spin pair, and this averages out their noise. And a combination of those 3 factors leads to this pretty impressive coherence time. So to conclude, we've shown that we could strain tune the optical transitions of the SIV, which is important if you want to optically interface several of them in a quantum network. We eliminated the dominant source of dephasing at 4 Kelvin, which is phonon-induced decoherence. And we showed on the way that the SIV has an impressive strain susceptibility that we took advantage of to perform mechanical control of the SIV spin, did mechanically control of the nuclear spin, showed that the nuclear spin keeps its long coherence times. We only used 2 orders of magnitude less power, which is good for future scale-up. And finally, this control method, because it only relies on the dipolar coupling between the nuclear spin and the SIV spin, is applicable to any nuclear spin, which is different to some other nuclear spin control methods with electric field, for example, or even mechanically, that require quadrupolar effects. So in the outlook, we would like to incorporate such mechanical driving system with photonic structures that would allow us to extract photons more efficiently. We could also use strongly coupled nuclear spin from the host silicon-29, which has a nuclear spin 1/2. And this would allow for even faster control and even potentially the realization of a swap gate between the nuclear spin and the electronic spin. We could also incorporate the SIV center into a mechanical resonator that in the long run could be cooled down to the ground state level. And so if we could reach the single phonon regime, we could even try to store single phonon states into a long-lived nuclear spin. And so to conclude, I'd like to thank the group of Mete Atatürk in Cambridge with Christian Hepp, which was also participating in the study, Mustafa Gündoğan and Camille Stavrakas. And on the Harvard side, now Professor Yongik Son, Surjan Mesala, and Smarak Maiti, with whom all these experiments were performed. And I'd like to thank you for your attention.
Thank you for giving a very nice talk. Let's have a question from the audience. If there's no question from audience, let me ask what I was curious about. So looking at all these great results, it's very exciting, and actually the progress is like much faster than I was imagining. So recently was the famous work from the Team Tamnius group is that work called the DDRF gate, where he entangled more than I think 5 or 7 qubits using multiple nuclear spins. But that work was done with the NV Center, and I wonder if there is any like route to build upon that work using your system, like surface acoustic wave or silicon vacancy color centers.
So that's a good question. This DDRF system was relying on the nuclear spins were directly driven using an RF. So in this case, that wouldn't work because you need to go through the SIV to perform those measurements. But you could apply this DDRF system to the SIV, but this time you'd be driving the nuclear spins directly with a RF.